Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, we're very pleased to have Alex Walitsky, is that how your name is pronounced? From MIT. And he is going to be talking about reputational bargaining under knowledge of rationality.
All right, thank you very much for the introduction, and thank you all for coming. It's a pleasure to be here. So today I'll be talking about my research on, like Jennifer said, reputational bargaining under knowledge of rationality. Okay, so this paper is about bargaining, and in bargaining, it's often important to convince one's opponent that one's committed to a strong bargaining position. So I'm going to start with this quote from Thomas Schelling, who is an economist and political scientist, who was sort of one of the first people to think about bargaining in that way. So here's a quote from him about labor negotiations. He says, "It's not been uncommon for union officials to stir up excitement and determination on the part of the membership during or prior to a wage negotiation. If the union's going to insist on $2, and efforts made to persuade the membership not only that the management could pay $2, but even perhaps that the negotiators themselves are incompetent if they fail to obtain close to $2. The negotiators reduce the scope of their own authority and confront the management with the threat of a strike that the union itself cannot avert." So the point of this quote is that convincing your opponent that you're committed to a strong bargaining position can be important, but in reality, a bargainer might not know exactly what her opponent believes about her, and therefore, say, might not know what it would take to convince her opponent that she's committed in this way. So here's Schelling again. Here it's by no means easy to establish the commitment, nor is it entirely clear to either of the parties concerned just how strong the commitment is. So I've been talking about these issues today, and there's a sort of existing framework in game theory that models bargaining in this way, and this is the literature on reputational bargaining. So let me just briefly describe sort of how these existing models go in the literature, and then I'll talk about what I'll be doing differently today. So the idea here is that before the players start bargaining over, say, a unit of surplus, the players might be committed to different bargaining postures, which are, say, shares of the demand shares of the surplus that they're going to demand with some probabilities, say ex ante at the beginning of the game. And then the sequential equilibrium of these games proceeds like a war of attrition in the following sense. So each player is going to mix between mimicking this strong bargaining position, which is, say, sticking with this share of the surplus, and giving in and accepting her opponent's demand. And so when players behave like this, as long as a player mimics a bargaining posture rather than accepting, she's going to build reputation for being committed to this posture. So what does that mean exactly? So throughout this talk, when I mention a player's reputation, this is going to be her opponent's assessment of the probability that she's committed. So right again, there'll be these two types of players, those that are committed to playing in a certain way and those that can those are rational and can choose freely. A player's reputation is her opponent's view of the probability that she's committed. And so, in an equilibrium like this, there are two things that can happen. A player can accept her opponent's demand. That only happens in the event that she's not committed. Or she can follow this tough posture, and that can happen if she is committed or if she's not committed. So by Bayes' rule, as long as a player follows the tough posture, her opponent's assessment of the probability that she's committed to this posture is going to increase over time. And so that's what I mean by a player building reputation by mimicking a bargaining position, or bargaining posture, say. And so if a player does this for long enough, eventually her reputation for being committed is going to reach 1. At that point, her opponent's going to be convinced that she's committed, and her opponent's only rational action at that point is going to be to accept her demand and give in. Yeah.
Is this one bargaining interaction, or this is a sequence of different bargaining?
So it's one bargaining interaction, but the interaction could take a long amount of time. Exactly. So today I'll be talking about reputation within one bargaining interaction.
Commit to the bargaining posture. I'm committing to my whole strategy.
Exactly. Yes, that's how it's going to be. Yeah, I'll describe the model in more detail, but that's how it works, both in these existing models and in what I'll be talking about today.
Do you pay anything by waiting? And does it cost you to wait?
Yeah. They'll be exactly. But again, this will all become clear sort of when I get to the more formal model. And so then in these models, the players' equilibrium paths can be determined by their relative patience and their relative commitment probabilities. Okay. So as I highlighted, the sort of existing literature on this kind of bargaining looks at sequential equilibrium. And roughly that's, I guess, in the question, when players know each other's strategies, what bargaining postures do the players adopt, and how's the bargaining surplus divided? So today I'm going to look at a similar model, but I'm going to ask a different set of questions. So rather than ask what happens in equilibrium, I'm going to characterize what I'll call the player's Maxmin paths and postures. In other words, I'm going to ask the question, when players only know that each other's rational, but don't know what their opponents believe about them or exactly how their opponents are going to bargain, what bargaining posture for each player guarantees her the highest share of the surplus, and how much is each player guaranteed to receive? So the idea is that this is going to complement this existing equilibrium analysis by deriving bounds in the paths that the players can receive that hold even out of equilibrium, and by identifying bargaining strategies for each player that do well robustly, and that they do well for any rational response of one's opponent. And this is also going to model this uncertainty about one's opponent's beliefs and strategy that I argued was often important in bargaining. Are there any questions?
More realistic in the existing literature. Are there any real-world situations that correspond to knowing each other's strategies?
Well, so I think, for example, you might think that if you've played each other for a long time, you might learn how the other one plays, and play might sort of converge to equilibrium in a sense. So in that sense, you could think about what I'm doing today as maybe perhaps being better suited to a one-shot interaction where you haven't yet had time to learn how the other one's playing.
So in the existing literature, do people actually come up with the dynamics which actually proves or motivates what you just said, or is that just cheap talk?
No, I mean, so essentially, like, the existing equilibrium, the existing literature looks at what happens under this strong assumption that play satisfies the sequential equilibrium. They make very precise predictions about how bargaining goes and about how the surplus is divided. Today I'll be making weaker assumptions, and I'll make correspondingly weaker predictions, but I'll argue that the predictions I can make in these weaker assumptions are still interesting. So, yeah. Okay, so let me just let me just preview the model I'm going to talk about today. I will go through this more formally later, but just to give us a bit more sense of what's going on. So there are going to be two players who are each going to announce arbitrary dynamic bargaining postures. And a bargaining posture is just a plan for what you're going to announce, for what you're going to demand at each point of the negotiation. So for example, a union could announce that it's going to demand $2 an hour at every point in time. So if you don't give it $2 today, it's going to continue to ask for $2 tomorrow. It could also announce that it's going to demand $2 an hour today, and then subsequently demand $2 an hour plus compensation for the cost of the strike thus far. Or it could announce, of course, any number of other more complicated bargaining postures. I assume that whatever bargaining posture a player announces, she becomes committed to bargaining in that way with some fixed exogenous probability epsilon. So the player makes a speech, and then she finds out with some probability epsilon whether this speech binds her or not. And if it does, she must bargain this way for the entire negotiation. If not, she can bargain freely and change her offer however she wants. So a player is going to know that her opponent knows that she's committed to the bargaining posture she announced with at least probability epsilon. And she'll also know that her opponent's rational in that whatever belief her opponent has about how she's going to bargain, he plays a best response to that belief. And he also updates his beliefs according to Bayes' rule. But she's not going to know anything else about her opponent's beliefs or her opponent's strategy. And the player's then going to bargain over a unit of surplus in continuous time, and the offers are going to be unrestricted, and that players can change their demands at every point in time. So in particular, nothing here is going to be driven by, say, the order or relative frequency of offers, unlike in some other bargaining models.
I still don't understand. You have sort of this one person which has a probability, but they're bargaining with somebody. Is that somebody just a machine and has no probabilities and no commitments?
So in general, the model is going to be symmetric. Both players are going to make these announcements, then both players are going to be able to change their offers. Though actually, for most of the analysis, I'll focus on a case where only one player gets to make this announcement, but I'll then show how that carries over to the case where both players make announcements.
The announcement is only made once.
Exactly. So this is a crucial point. The announcements are made once at the beginning of time, so it's as if before we start bargaining, I get up in front of the union rank and file and say, I'm not going to settle for less than $2 an hour, and then maybe that commitment binds me, in which case it binds me forever, or maybe it doesn't, in which case I bargain freely forever. But the commitment happens once and for all at the beginning of the game. Yeah.
So there's no modeling of like just retweet but then commit again also.
Exactly. Yeah, I think that would be sort of an interesting extension to see what if you could try to recommit yourself later on, but I'm not talking about that today, and I don't study that in the paper. And so then, again, the goal is going to be to characterize the highest payoff that a player can guarantee herself, and it turns out that this can be thought of equivalently as the highest payoff a player can receive when she's pessimistic about her opponent's strategy or her max-min payoff. So sort of the max-min and min-max are actually going to be the same in this model. Okay, so to preview the results, in the benchmark model where only one player announces a bargaining posture, I'll show that if this player has even a small chance of becoming committed to her announced posture, she can guarantee herself a large share of the surplus. So for example, if a player's commitment probability is 1 in 10, she can guarantee herself approximately 30% of the surplus. And even if her commitment probability is only 1 in 1,000, she can still guarantee herself about 13% of the surplus. And furthermore, the unique bargaining posture that a player has to announce in order to guarantee herself this much is simply initially demanding this share of the surplus and subsequently demanding compensation for delay in reaching agreement. So this is like saying that perhaps the union can't guarantee itself $2 an hour by announcing it's going to demand $2 forever, but can by announcing it's going to demand $2 initially and then subsequently demand $2 plus compensation for the cost of the strike. So I think this is a somewhat striking result. So the first part says that there's a single strategy that a player can adopt that guarantees her a large share of the surplus for any rational response of her opponent. And, oh, okay?
Like, just to understand, is there is like if she gets less than 50% of the surplus, that means that the opponent got more than her, or does it? Is the goal here to get more than 50% of the surplus, or the goal is to get more than 0%?
So the goal is just to get as much as you can. And what I'm saying here is that even if I don't know exactly what your strategy is, what you believe about me, there's one strategy I can follow that guarantees me, say, 30% of the surplus when my commitment probability is 1 in 10, regardless of whatever rational response you play to that strategy.
And he's asking, does the other player get the 70%?
Oh, I see. So not necessarily. So for example, with two players, each player will be able to guarantee themselves 30%, but I won't say exactly what happens. So predicting exactly how bargaining is going to proceed is going to depend on other assumptions, say about the player's beliefs and strategies. On the other hand, I will be able to say something about how bargaining proceeds. So for example, if each player gets at least 30%, there can't be, say, so much delay that more than 40% of the surplus gets burned.
Two things don't add up to more than 100%.
That's right. That's right. They don't add up to more than 100%, but they can add up to less than 100% if there's delay. Exactly.
So you gave us a few numbers. What if I commit with 50%? Do I guarantee myself 50% of the share?
No. So I'll present the formula for what you get for any commitment probability.
Wants to know if there's like an asymptotic value maximum or something. Yeah.
Oh, I see. So at least in this benchmark case where only one player makes an announcement, as your commitment probability goes to 1, you can guarantee yourself the entire surplus. Because it's sort of as if you could make a take it or leave it offer in a sense. And so for example, if I said I want 99% and you were sure that I was going to ask for 99% forever, you would have to just give in and give me 99%. Because rejecting would only lead to delay. It would never get you any more of the surplus. So I've mentioned how this bargaining posture that guarantees the highest share of the surplus is similar to this behavior of unions of demanding a fixed wage plus pay for the strike. It's also similar to behavior you see sometimes in torts trials where generally the defendant's liable for the initial damages plus interest that accrues until the judgment's handed down. This can be thought of as the plaintiff demanding the initial damages plus compensation for delay in settling the claim. And so I'll spend most of my time discussing this main result. In this case where only one player makes an announcement, I'll then show how this extends to the case where both players make announcements. Okay. So to make this a little more concrete, let me just talk about a simple example. So again, consider this benchmark model where one player makes an announcement. And suppose that the credibility for an announcement is 1 in 10. So whatever announcement she makes, she becomes committed with probability 1 in 10. And let's say that the common discount rate R here is just 1. So then the player with commitment power can guarantee herself about 30% of the surplus by announcing the following bargaining posture. So she announces that at the beginning of time, she's going to demand 30% of the surplus. And then subsequently, her physical demand is going to increase over time at a rate equal to the discount rate, which here is just 1, in order to compensate her for the delay in reaching agreement, until such time as she's demanding the entire surplus, and then from that point on, she demands the whole surplus forever. And so this is the unique bargaining posture that she can announce in order to guarantee herself 30% of the surplus. One thing to note here is that the discount rate plays essentially no role here. So the amount that a player can guarantee herself is independent of the discount rate, and changing the discount rate would change this picture only by renormalizing the time axis. So I've mentioned how this paper is related to the existing literature on reputational bargaining. It's also related more broadly to the literature on commitment tactics in bargaining, again dating back to Schelling. And finally, it's related to the literature on bargaining with incomplete information, either without common priors or without equilibrium, in the sense that in all of these cases, the players can disagree about the probability distribution over outcomes of bargaining. Okay, so I'll start by presenting the formal model where only one player makes announcements. I'll then present the main result of this paper, which is a characterization of a player's Maxmin, Payoff, and posture in this model. I'll spend most of the time discussing that result. I'll then quickly say how this extends to the case where both players can make announcements, and finally I'll conclude. Are there any questions before I get into the model? Okay. Okay, so there are going to be two players, and throughout player 1 is going to take female pronouns and player 2 male pronouns, and they're going to bargain over one unit of surplus. And the bargaining is going to proceed in two phases. So before the players actually start bargaining, there's what I'll call this commitment phase, where again, for now, only player 1 is going to announce a bargaining posture. I'll denote this by gamma, and this is just a map from times to what the player says she's going to demand at that time. So just a map from times to shares of the surplus. And I assume that whatever bargaining posture player 1 announces, with probability epsilon, she becomes committed to that posture. And that means that at every time t, she has to demand exactly gamma of t, exactly what she said she was going to demand. And she always rejects her opponent's demand. She always holds out for her opponent to accept her demand gamma of t. So after these announcements, the players bargain, and time runs continuously from 0 to infinity. And at every point in time t, each player I makes a demand ui of t, which is just the share of the surplus that she's asking for at that point in time. And she also decides whether or not to accept her opponent's demand uj of t. And the game ends whenever some player I accepts her opponent's demand ujt. In that case, player j, the player whose demand was accepted, gets exactly what he was asking for, uj of t. Player I gets what's left over, 1 minus uj of t. And both players discount their payoffs at the common discount rate r. Okay. So now to complete the description of this model in continuous time, there are a couple technical issues that have to be addressed. Yes, R is common knowledge.
Once apart from this, if with probability 1 minus epsilon, they both are just rational and they have the same. They just want to maximize the income.
Exactly. So you make this announcement at the beginning of time, and then with probability epsilon, you become committed. And what that means is that at every time t, you demand gamma of t, and you never accept your opponent's demand. With probability 1 minus epsilon, you don't become committed. And at that point, and in that case, you can follow any strategy in the bargaining phase. So you choose your demand uit at each time t completely freely, and you freely decide when to accept your opponent's demand.
Sorry, epsilon is a parameter or something?
Epsilon is a parameter, exactly.
To make it to 0 in the end, to do again, like in the limit.
So as epsilon goes to 0, your announcement is going to be meaningless, and your opponent's beliefs won't be constrained at all. In that case, you can't guarantee yourself anything. So what'll be interesting is that for small but non-zero values of epsilon, you can guarantee yourself a lot. I think epsilon is being relatively small. So these numbers like 1 in 10, 1 in 100, 1 in 1,000, something like that. Right. Okay. So again, to complete the description of the model, formally we have to deal with some technical issues that aren't going to play a big role in the talk today, but I just want to briefly highlight them here so we have a better sense of what the formal model is in the paper. So the first is that there are these fairly standard measurability problems that arise in continuous time modeling. The issue is that a strategy profile for the players might not uniquely determine an action path. So to deal with this problem, I restrict the players to revising their paths of demands at integer times. So players' demands change continuously, but they have to choose their path of demands for the next integer on the integers. This is really a mathematical restriction rather than economic restriction. The reason is that how far apart the integers are from each other has no meaning independent of the discount rate, and the results here don't depend on the discount rate. I also assume that the player's paths of demands have to be continuous at non-integer times. And the second technical issue is that the set of times which a player can accept her opponent's demand might not be compact in general, which can lead to players not having well-defined best responses. To deal with that, I just, for every time t, introduce a date t minus, interpreted as just before time t, at which a player can accept the limit from the left of her opponent's demands. So what this is just saying is that if your demand jumps at time t, then at time t, I have the choice of accepting either one of your demands.
Are your measurability problems just problems to... Are there real problems, or are there problems where you say, I don't want to deal with them? In other words, if you were willing to go into super processes and whatever, you could get around them. It's just so heavy machinery that you say we don't learn anything from it.
So I show in the paper that all the results that I derive in this continuous time model also hold as you take a discrete time bargaining game and then take the limit as players' offers become frequent, however you take that limit. So you can think of this model as sort of the limit of discrete time models. I'm not sure if that exactly answers your question.
We should do this offline.
Let's do it offline.
Yeah.
Okay, great. All right. Okay. Okay, so are there any questions on any further questions on the model? Okay. All right, so this slide is notation heavy, but this is essentially all the notation we're going to need, so it'll be rewarding when we get through this. So, so capital sigma I is going to be the set of playerized bargaining phase strategies, sigma I. Pi I is going to denote a probability distribution over sigma j. This is going to be playerized belief about player j's bargaining strategy. So all the uncertainty in this model is strategic uncertainty. What I'm uncertain about is the strategy that you're playing. And so this is modeled in this way. UI of sigma I sigma j is playerized payoff given strategy profile sigma I sigma j. The expectation of playerized payoff with respect to her belief pi I is just denoted E pi I of UI sigma I sigma j. And finally, sigma I star of pi I is the set of playerized best responses to her belief pi I. Are there any questions on this slide? Okay. So the key innovation of this paper relative to the existing literature is the solution concept I'm looking at. And so let me carefully define this. Heuristically, what I'm looking for is a player's Maxmin payoff, which is the highest amount she can guarantee herself when all she knows about her opponent is that he's rational and that he knows that she follows her announced bargaining posture with probability at least epsilon. And also a player's Maxmin posture, which is what she has to announce in order to guarantee herself that much. Okay, so what does this mean formally?
So you're saying that this is a new solution concept?
So this is actually going to be, this isn't exactly a new concept. So what I'm looking for here is the highest payoff, the lowest payoff a player can receive when the only assumption is knowledge of rationality, that she knows her opponent's rational. But I'm just going to sort of go through the definition here carefully to try to make it clear what we're talking about. Right, so it's not a new solution concept, but it's new to apply it in this class of models. Okay, so what does it mean that player 1 knows that player 2 is rational? So formulas say that a strategy sigma 2 of player 2's is rational given the posture gamma that player 1 announced if there exists some belief pi 2 of player 2's that assigns probability at least epsilon to player 1 following her announced bargaining posture gamma that rationalizes sigma 2 in the sense that sigma 2 is a best response to pi 2. So after player 1 announces a bargaining posture gamma, that she knows that player 2 is rational means that she knows that he's playing some strategy that satisfies his definition. I'll call capital sigma 2 gamma the set of player 2 strategies that are rational given posture gamma. And so therefore, that player 1 knows that player 2 is rational means that she knows that he plays some strategy in this set. So therefore, the highest amount that player 1 can guarantee herself after announcing any arbitrary bargaining posture gamma, I'll denote by U1 star of gamma. This is just the highest amount that she receives when she follows some strategy sigma 1, and player 2 plays his worst rational response to sigma 1. And then finally, player 1's overall Maxmin payoff is the highest amount she can guarantee herself at the beginning of the game. Okay. I'll say that a bargaining posture gamma star is a Maxmin posture if there exists a sequence of bargaining postures gamma n converging pointwise to gamma star, such that the Maxmin payoff given posture gamma n converges to the Maxmin payoff. So you might wonder why I have to define this like this rather than saying that a posture is a Maxmin posture if it maximizes the Maxmin payoff given that posture. The reason is that the latter set might be empty because of an openness problem that's standard in bargaining models. So to see what this problem is, you can just think about ultimatum bargaining, where the players have to divide a surplus, and player 1 demands a share of the surplus, and player 2 can just accept or reject, and if he rejects, they both get nothing. So in that case, if player 1 demands any share of the dollar except the entire dollar, player 2's unique best response is to accept, and so player 1's guaranteed what she was asking for. But if player 1 demands literally the entire dollar, then it's also best response for player 2 to reject. So in the sense, player 1 wouldn't be guaranteed the whole dollar. So these definitions are just like saying that in that game, player 1's Maxmin payoff is the whole dollar, and her Maxmin strategy is demanding the whole dollar. And so this limiting definition is going to be needed in exactly the same sense here. Okay.
Which is why you'll see things like 99 cents, basically, in a real situation like that, right?
Right, sure.
And then you're kind of trying to approach that.
Exactly.
Wait a minute, did you just say that the result of this definition is that player 1 should demand the whole dollar?
Oh, well, exactly. So, right, exactly. So the definition
is...
is...
That's not the right answer.
Excuse me?
But that's not the right answer.
It's asymptotically, and that's why he puts in this definition.
Yeah.
And it's not accounting for the fact that players have egos.
So I understand that. So gamma star doesn't tell me what I should actually do.
So actually, in the proof, or in the argument here, I'll describe postures that get you arbitrarily close to the Maxmin payoff. And what they do is they approach gamma star. Exactly.
Gamma star is not, just to be clear, gamma star is not necessarily what I should actually do.
Right, but it's what
Even though you might have thought that.
Exactly.
Right.
Exactly. Right. Exactly. So maybe actually you should demand your U1 star minus a penny, and then.
Right, and that's why also Christian was asking about the dynamics that approach this, and right, I mean, is there a dynamics which approaches the right answer?
I see.
Yeah.
Okay. Are there any more questions on this definition?
So the two players are somewhat different. The player one is the player one is not okay. So player two, the strategy is completely determined by its belief on player one. Well, player one with probability epsilon has this exogenous strategy that is committed to, and other than that, he's doing like best response to the belief.
Exactly. Yeah. Okay.
Can you go back? Why is it in? I mean, what you're essentially saying there is that player 2 will react to player 1's strategy, so he will try to get the infimum for player 2, and then player 1 will try to do the sigma, which makes it maximal for him. But why is it not the other way around? Who says that the reaction is not of player 1 to player 2 strategy?
I see. So again, here I'm not sort of trying to predict how bargaining is actually going to go. I'm saying how much can player 1 guarantee herself, and how does she guarantee herself this much? So I'll ask the analogous question for player 2 also later. Okay. So a final reason why I'm looking at this Maxmin payoff is that any payoff above a player's Maxmin payoff can result from her best responding to some rational strategy of her opponents. So in this sense, a player's Maxmin payoff determines not only the lowest amount that she can receive under knowledge of rationality, but actually the entire range of payoffs that she can receive under knowledge of rationality. So formally, for any bargaining posture gamma and any payoff U1 greater than player 1's Maxmin payoff given gamma, there exists some rational strategy of player 2's such that when player 1 best responds to this strategy, she gets exactly U1. Okay. So again, the point of this is just to further motivate why we're looking at a player's Maxmin payoff. Okay. So now I'll present the main result of this paper, and this is the result. So when player 1's commitment probability is epsilon, her Maxmin payoff is exactly 1 over 1 minus log epsilon. And in addition, her unique Maxmin posture gamma star is given by initially demanding her Maxmin payoff U1 star. Subsequently, her demand subsequently increases in order to compensate her for delay in reaching agreement. That is, she demands e to the RT U1 star until this amount reaches 1, and subsequently she demands the entire surplus forever.
Now, if the two players have different discount rates, is this also one of the player who's of player 2, or is it more complicated?
So in the paper, I talk about what happens when the players have different discount rates. So what's going to happen there is the more player patient is going to be able to guarantee herself more of the surplus, so she should initially demand more. And then she should again demand enough to compensate her for delay in reaching agreement. So her demand should increase at her own discount rate.
Or at her own?
Exactly.
So she doesn't have to know the discount rate of player 2?
She doesn't know to know how much she can guarantee herself. So her initial demand is going to depend on player 2's discount rate, but the rate at which her demand increases is just going to be her own discount rate.
Just the formula for U1 star will be more complicated. Gamma star is the same.
The same with that R being R1.
R1.
Exactly. Okay. Okay, so again, there are two things to notice about this result. So the first, that a player's Maxmin payoff is large relative to her commitment probability epsilon. So when a player's commitment probability is small, roughly speaking, her commitment probability has to square in order for her guaranteed payoff to divide by 2. So I said that a player is guaranteed 13% if her commitment probability is 1 in 1,000. She's guaranteed 7% if her commitment probability is 1 in 1,000,000. And in addition, the Maxmin posture is simply saying, I want my Maxmin payoff, and if you make me wait to get it, then you have to compensate me for the delay in reaching agreement. So I won't have time to prove this result today, but I'll spend most of the remaining time discussing why it's true. So first I'll talk about why the Maxmin posture takes this form. That argument's going to take 2 steps. So the first step is going to be saying, for any bargaining posture gamma that player 1 announces, what's the worst belief that player 2 can have about how player 1's actually going to bargain? And then once I answer that question, I can ask what bargaining posture should player 1 announce, given that player 2 is subsequently going to have those worst possible beliefs. And then finally, I'll talk about why the Maxmin payoff equals 1 over 1 minus log epsilon. Okay. Are there any questions before I get into the argument? Okay.
Gauss belief is not just with, that with probability epsilon, 1 minus epsilon is going to give me anything? Or it's
Say again?
the worst belief for player 2 is not that with probability 1 minus epsilon player 1 is going to demand 0? Or it's
Exactly. That's actually an interesting question. So the question is, well, why isn't the worst just that with probability epsilon you'll stick with this thing you announced, with probability 1 minus epsilon you'll give in and give me everything today? So these said if player 2 had those beliefs, then if player 1 didn't give in immediately, player 2 would update and learn that player 1 is actually committed for sure. And so all player 1 would have to do would be to reject for an instant, and player 2 would learn she was committed and give in. So actually those beliefs would be quite good for player 1. Right, exactly. So this kind of argument is actually exactly going to be what plays a role in the proof. Okay. So again, the first question is, given that player 1 announces some bargaining posture gamma, what's the worst belief that player 2 can have about how player 1 is actually going to bargain? And I'll call that the gamma offsetting belief. Okay, so the first important fact is that player 1's Maxmin payoff given posture gamma, which recall is defined as the highest amount that player 1 receives when she chooses any strategy sigma 1, and then player 2 chooses his worst rational response sigma 2, is actually exactly what player 1 gets when she follows her announced bargaining posture gamma forever, and player 2 plays his worst rational response to gamma. In other words, this is saying that in order for player 1 to guarantee herself as much as possible, she should always follow whatever bargaining posture she announced after she announces that. The reason for this is that if once player 1 deviates from her announced bargaining posture, then subsequently player 2's beliefs about how she's going to bargain are unrestricted. And so, for example, player 2 might think that she's going to give him the entire surplus, and so he might not give her anything after that point. So because of this, from now on I'm going to talk about player 1's announcement, player 1's posture, and player 1's demand interchangeably. With the
Is
epsilon known to player 2? I think the way to think about it is yes, but again, like essentially all that matters here is from player 1's perspective, how much can she guarantee herself? So really what matters is when player 1 makes an announcement, with what probability does she believe that player 2 believes that she's following this strategy? But I think probably it's easy to think about epsilon as being known, commonly known, say, between the players.
So what you say is if you commit even with probability epsilon, you're actually better off just following through with your commitment and all.
Exactly. So right. So what this is saying that in order to guarantee yourself as much as possible, whatever bargaining posture you announce, you should then follow that bargaining posture forever. No, because so there's one sense in which it's similar to that, because in both cases, so there's whatever posture player 1 announces, she wants to follow it whether or not she's committed to it. So from player 1's perspective, maybe it would be okay if epsilon were 1. But the key is, what does player 2 believe? And epsilon is crucial in determining that. So player 1 could guarantee herself much more if epsilon was higher, say.
Does player 2, are we assuming that player 1, does player 2 get to assume that player 1 is rational?
Exactly. So we're not assuming that now. So it turns out that assuming that won't affect the results. So what I'm assuming here is that just first order knowledge of rationality. Player 1 knows that player 2 is rational, but not necessarily player 1 knows that player 2 knows that player 1 is rational. On the other hand, if you did impose those assumptions, it turns out that player 1 couldn't guarantee herself more even under those stronger assumptions. But here I'm allowing player 2 to hold any belief about player 1.
What you really mean is that he's following his bargaining strategy, except possibly accepting an offer from player 2?
No. So in order to guarantee as much as possible, player 1 just needs to stick with gamma forever. That's what this is saying.
Gamma asked for too much.
Okay.
Say, you told me I can get 30%, but I've only used this on a gamma where my initial posture is 70%.
Right. So if I announce 70%, then after making that announcement, the way that I guarantee myself as much as possible is by sticking with the 70% announcement. Right? Because if I then went back to 30%, that wouldn't be any good for me, because you still think that now maybe I'm committed to 70%.
I accept that you can't answer that. So it doesn't matter what you think afterwards. Accepting an offer ends the game, right?
Oh.
Make me an offer and I accept. That ended the game.
Okay, I see. So I see what you're saying. Okay.
Accepting an offer.
Exactly. So if I announce some bargaining, some strategy gamma, following gamma forever might not be a best response to any strategy of yours, but it is a best response to the worst possible strategy of yours, and that's what matters for determining how much I'm guaranteed. Did I answer the other question?
No. I'm still confused, but maybe you should press on.
Okay, maybe if you're still confused later, we can come back to it. Okay. Okay, is this clear, at least, what this is saying? So this is saying that when we're determining how much player one can guarantee herself, we can think about her posture and her demand interchangeably. She should always just follow her posture to guarantee herself as much as possible. So therefore, I'll call a strategy sigma 2 of player 2's that minimizes player 1's payoff when she mimics her announced posture gamma, the gamma offsetting strategy. This is the worst strategy that player 2 can follow from player 1's perspective. And I'll call a belief pi 2 of player 2's that rationalizes this strategy, the gamma offsetting belief. So this, again, is the worst belief that player 2 can have about how player 1's actually going to bargain. Okay, so what is this belief? So in general, player 1 might announce a bargaining posture such that player 2 rejecting her offer might actually be good for her. Right, so if player 1 sort of demands too little, then if player 2 accepted, this might be bad. But here I'm not going to focus on those sorts of postures. I'm going to focus on the more typical case where it's bad for player 1 when player 2 rejects her demand. So this is the case, obviously, if player 1 announces a posture that demands a constant share of the surplus, then the longer player 2 rejects, the worse it is for player 1. So I'll think about that case here, and I'll ask the question, for how long can player 2 rationally reject player 1's demand for? So if player 1 announces gamma and then mimics gamma forever, how long can it be before agreement is reached? Okay. So for player 2 to reject player 1's demand at all, he has to be optimistic about player 1's future play. If he thinks that player 1's never going to offer him more, he needs to accept today because rejecting is only going to cause delay and maybe lead to a worse offer. So player 2 is only going to reject player 1's demand if he expects player 1 to give him future rewards. Okay. But whenever player 2 expects a reward from player 1, then when player 1 doesn't give him this reward, which is what happens when player 1 mimics her posture gamma, player 2 updates that player 1's more likely to be committed to gamma. Because this posture gamma doesn't give these rewards, so if I expect you to give the rewards and you don't, I learn that you're more likely to be committed. So therefore, if I expect you to give these rewards more frequently, then when you mimic gamma, you build reputation more quickly. And building more reputation more quickly is good for you, because when your reputation reaches 1, I have to accept, because at that point I know you're committed. So therefore, it's always going to be worse for player 1 if player 2 thinks that she rewards him by giving him one big concession rather than several small concessions. Because if
I should have asked it much earlier. Do I throw in each round a coin and sort of with probability epsilon I'm committed, or does beforehand God throws a coin and I now know that actually I'm committed or not, and that probability was epsilon?
So the commitment or not commitment just realizes only once at the beginning of the game. Okay.
So as player 2, I only have to figure out in which state of the world we are. And
exactly.
And I will update my probability deciding what state are we in.
Exactly. Well, so that's right. But again, here I'm allowing player 2 to have player 2's beliefs essentially are restricted by the fact that he knows that player 1's committed with probability epsilon, and with 1 minus epsilon, he could believe anything about how player 1 plays. So I think so what you said is correct in that there are these 2 states of the world: player 1 is committed or uncommitted. But player 2 essentially is trying to learn player 1's strategy, and he can believe that player 1's following a range of things. Is that clear?
So he has to learn player 1's strategy, but also whether player 1 is actually committed or not, right? Because
so in a sense, all that player 2 cares about is what strategy player 1 is following.
I see.
Okay.
So is the family of distribution you're looking at, there is a distribution that you say you follow gamma until time t, and then time t you give up and you give everything? And that's what player 2 believes about player 1, that it's some distribution over this time t?
So what I'm characterizing here are the worst beliefs that player 2 could have about player 1. Is that what you're asking about?
Yes.
Okay. So you could think about it. That's a fine way to think about it. I mean, the way I'm sort of describing it here is that player 2 thinks that either player 1's committed or player 1's mixing between mimicking the committed type and giving up. But you could also think that player 1's following, this continuum of strategies that each have one time which they give up for sure. That's equivalent.
So it's like a probability over, say, the integers, where
Or over the
Ability,
reals.
you-
Remember,
you
player one can give
follow
it any
until
time.
t, and then you're gonna give up.
Sure, yes, okay. But, right, player one can give it at any time, not just at integer times. Okay. Okay. Okay, so just to... So again, it's worse for player one when player two thinks that when player one deviates from her announced posture, she does this by giving up to player one, by giving him everything. Because if you thought that instead she would maybe give him a series of small concessions, that would let her build reputation more quickly, and that would be better for her. Okay, so this slide has been a bit heuristic, but the conclusion is that player two is going to reject player one's demand for as long as possible when he believes that player one concedes the entire surplus to him at the slowest rate that makes him willing to reject her demand. So this is getting back to the earlier question about what's the worst thing for player two to leave about player one. If player two thinks that player one's conceding too quickly, this is actually good for player one, because then player one can build reputation quickly by not giving up. Okay. Okay. Okay, so now the question is, what is this rate? What's this slowest concession rate of player one's that makes player two willing to reject her demand? Okay, so let's characterize that now. I'll call that lambda t, this rate. Okay. So if player two accepts player one's demand of gamma t, he gets what's left over, 1 minus gamma t, and this gives him flow payoff r times 1 minus gamma t. On the other hand, if player two rejects player one's demand, then at rate lambda t, player one concedes to him and gives him the entire surplus, which is worth 1. On the other hand, he could always have accepted player one's demand of gamma t and gotten 1 minus gamma t, so this concession overall is worth to him lambda t times gamma t. In addition, the amount that player one is offering him gamma t is changing over time, and he has to take this into account when computing his flow payoff from rejecting her demand as well. So overall, his flow payoff from rejecting her demand is lambda t gamma t minus gamma prime of t. And setting these two expressions equal to each other yields the lowest concession rate lambda t that makes player two willing to reject player one's demand. This is given by this formula here. So the key thing to notice about this formula is that the rate at which player one has to be conceding to make player two willing to reject her demand is very high when player one's current demand gamma t is low. And that's actually very intuitive. What that's saying is that if I'm offering you almost the entire surplus today, then in order for you to reject that, you have to think that I'm going to give up to you very quickly in the future. So you have a large amount on the table today. For you to spurn this, you have to think that good things are going to happen very quickly. So this is an important intuition here. Was that clear? Should I go through that one more time? Okay. 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 Okay, but all right. So the key thing here is that player one is going to build reputation more quickly when her demand is lower. Again, when player two has these worst possible beliefs. And so this is important because this gives player one a reason to want to demand as little as possible. The less she demands, the more quickly she builds reputation when her opponent has these worst possible beliefs. Okay, so this is what we need in terms of characterizing these gamma offsetting beliefs. Now we can ask what posture gamma should player one actually announce. Okay. So there are two key ideas here. The first is what I just said. Player one builds reputation more quickly when her demand is lower. And this makes her want to demand as little as possible to help her build reputation more quickly. On the other hand, she can't demand too little, because if she demands less than she's trying to guarantee herself, then her opponent could accept that demand. And that would leave her with less than she's allegedly guaranteed. So putting these two ideas together, it follows that any Maxmin posture of player one's has to demand exactly her Maxmin payoff plus compensation for delay, at least until her reputation reaches 1. So again, as long as she's building reputation, she'd like to demand less that she builds reputation more quickly, but she can't demand less than the level of utility she's trying to guarantee herself, because otherwise such a demand might be accepted. Okay. So this is probably the central intuition for why her Maxmin posture demands her Maxmin payoff plus compensation for delay. But this only says that she has to demand that much until her reputation reaches 1. It doesn't say what she might want to demand after that point. So let's denote by capital T the time which player one's reputation reaches 1 when her opponent has this worst possible belief. What might she demand after that time T? Obviously 1. Well, so for example, we haven't demonstrated that her demand is 1 at that point yet. For some postures, her reputation might reach 1 while she's still not demanding the whole surplus. Maybe I'll just go through it and we'll see if it becomes clear. Okay. Okay. So let's let T1 be the time which player one's demand reaches 1. So this is the point at which she can no longer demand any more compensation. And I claim that player 1's reputation has to reach 1 at exactly the same time which her demand reaches 1. So that is, this time t on the previous slide is to equal this time t1. Okay, so why is that? So let's suppose first that player 1's reputation reaches 1 before her demand reaches 1. So suppose she announces this posture, this black posture here that demands this initial amount plus compensation for delay, but that when her opponent has these offsetting beliefs, her reputation reaches 1 at the time indicated by this black line, which is before her demand reaches 1. Okay. So then suppose that instead of announcing this black posture from the previous slide, she instead announces this red posture that initially demands slightly more and then demands compensation for delay given this higher initial demand. So under this red posture, player 1's always demanding more than she is under the black posture, and therefore her demand reaches 1 earlier under the red posture than under the black posture. In addition, because she's always demanding more, she builds reputation more slowly, and therefore her reputation reaches 1 later when she announces the red posture than when she announces the black posture. On the other hand, both of these variables t and t1 change continuously in player 1's initial demand, so if she only demands slightly more initially, it'll still be true that her reputation reaches 1 strictly before her demand reaches 1. And you see that here. So therefore, when player 1 answers this red posture, her reputation reaches 1 at this time indicated by the red line. So at this point here, player 2 is certain that player 1 is going to continue following this red posture forever. And so at that point, player 2's only rational action is to accept, because he knows that if he rejects, he's only going to be offered less in the future and this will lead to delay. So therefore, when player 1 answers this red posture, she's certain that her demand is going to be accepted by this, at the latest, this time indicated by this red line. And up until that time, she's demanding full compensation for any delay. So under this red posture, player 1's guaranteed exactly her initial demand here, which is higher than she was guaranteed under the black posture. So this shows that it's not possible that under a Maxmin posture, player 1's reputation reaches 1 before her demand reaches 1. Okay, on the other hand, is it possible that her reputation reaches 1 after her demand reaches 1? Well, I've argued that player 1's demand has to increase all the way until her reputation reaches 1. And so if reputation reaches 1 after her demand reaches 1, she'd have to be demanding more than 1 at some point, and that's not possible. So that can't be the case either. It has to be that player 1's reputation and demand reach 1 simultaneously. So the only remaining question about player 1's posture is, could she ever demand less than 1 subsequently? So suppose that at some later time t, player 1's demand dropped below 1. Well, so then just before player 1's demand reached 1, her opponent at this point is being offered essentially 0. But he knows that if he waits until this future time t, he'll be offered something strictly positive, and so he should wait. And this is going to make player 1 worse off because she'll ultimately receive less and also is going to face some delay. So this is the intuition for why the Maxmin posture has to demand the Maxmin payoff plus compensation for delay until this reaches the entire surplus and then demands the entire surplus forever. Okay, so I haven't yet described so this is the intuition of the Maxmin posture. Now I'll describe why the Maxmin payoff equals 1 over 1 minus log epsilon. Where does that result come from? Okay. So let's just fix any initial demand u1 of player 1's, and let gamma be the posture that demands u1 plus compensation for delay. So the only difference between this posture gamma and the posture gamma star is that rather than initially demanding the max-min payoff, this posture gamma is just initially demanding some arbitrary payoff u1. And let's redefine these times t and t1 now with respect to this new posture gamma. So t is the time which player 1's reputation reaches 1, t1 is the time which her demand reaches 1, when she follows this posture gamma that initially demands some arbitrary amount u1 and then demands compensation for delay. So this posture gamma is one of these typical postures where delay is always making player 1 weakly worse off. Because under gamma, player 1 is demanding compensation for delay for a while and then demanding a constant amount. So delay is always making player 1 weakly worse off here. So therefore, the worst belief for player 2 to have is whatever belief makes him reject player 1's demand for as long as possible. That's the gamma offsetting belief. But we've already characterized that belief. That's the belief that player 1 concedes at this rate lambda t that we characterized earlier. Okay, so at any time at which player 1 is still demanding compensation for delay, this concession rate lambda t of player 1 simplifies dramatically, and this just becomes r e to the minus rt over u1. So now if player 2 has this worst possible belief, which is that player 1 follows her posture gamma with probability epsilon and concedes at this worst possible rate, then player 1's reputation reaches 1 at the time t given by this formula. So the right-hand side of this formula, epsilon, is just the probability at which player 1 never concedes to player 2's demand. That's the probability she's committed to this posture that never concedes. The left-hand side of this formula is the probability that player 1 doesn't concede to player 2 by time t. when she always concedes at this worst possible concession rate. So the time at which these are equal is the time at which the probability that player 1 hasn't conceded yet equals the probability that player 1's never going to concede. So at that time, player 2 is sure that player 1's never going to concede. In other words, he's sure that she's committed to this posture gamma. Okay. In addition, whenever player 1's reputation reaches 1 before her demand reaches 1, player 2 has to accept her demand as soon as her reputation reaches 1. This is by this exact argument I showed you before with this red posture. At this time t, player 2 is certain that player 1's demand is only going to get tougher over time, and so he has to accept her demand. And so because player 1's demanding full compensation for delay up until this point, in this case where player 1's reputation reaches 1 before her demand reaches 1, player 1's guaranteed her entire initial demand u1. Okay, so we now have a formula for the time at which player 1's reputation reaches 1. This was given by the previous slide. We have a formula for the time at which player 1's demand reaches 1. And comparing these two formula, we see that player 1's reputation reaches 1 before her demand reaches 1 whenever her initial demand is less than 1 over 1 minus log epsilon. And so because in this case player 1's guaranteed her initial demand, we see that as long as player 1's initial demand is strictly less than 1 over 1 minus log epsilon, she's guaranteed exactly her initial demand u1. So therefore, taking a sequence of initial demands converging upwards to 1 over 1 minus log epsilon yields a corresponding sequence of postures that converge pointwise to the Maxmin posture that I described earlier, such that the corresponding Maxmin payoff converges to 1 over 1 minus log epsilon. And so this proves that a player's Maxmin payoff is exactly 1 over 1 minus log epsilon, because I've exhibited a series of postures such that the corresponding Maxmin payoffs converge to this number. And in addition, if you believe me that the Maxmin posture is what I said it is, then it follows that the Maxmin payoff is actually exactly 1 over 1 minus log epsilon, because these postures converge to the Maxmin posture. And so this is the argument for why a player's Maxmin payoff is exactly 1 over 1 minus log epsilon. Okay. So I'm a little bit short on time, so I think so quickly, maybe it'll be helpful to just quickly show this graph. So this graph is a function of player 1's commitment probability epsilon, how much she's guaranteed, how much she can guarantee herself, both when she can announce any bargaining posture, this is given by this black line, and also by way of comparison, what she can guarantee herself when she can only announce bargaining postures that always demand a constant share of the surplus. That's what's given by this red line. So you see here that in both cases, player 1 can guarantee herself approximately the entire surplus as her commitment probably goes to 1. This is as if she can make a take it or leave it offer. In both cases, she can't guarantee herself anything when her commitment probably goes to 0, because in that case, her opponent's beliefs are unrestricted. And you see here there's a substantial advantage to player 1 to being able to announce a non-constant bargaining posture. Just to review the main result of the paper, I've shown that a player can guarantee herself a large share of the surplus even if her commitment probability is small. The intuition for this, again, is that a player builds reputation quickly when she's demanding little of the surplus. So even if her initial commitment probability is small, she can always compensate for this by demanding less. In addition, I've argued the unique bargaining posture that guarantees this much demands compensation for delay in reaching agreement. And that intuition came in two steps. The first idea is that demanding less is always going to accelerate reputation building on the part of player 1. But player 1 can't demand too little, or else her demand might be accepted. And finally, a player benefits substantially from being able to announce a non-constant bargaining posture. So in the couple minutes remaining, I just want to quickly describe how these results extend to the case where both players announce bargaining postures. So say now that player 1 announces a posture and becomes committed to this with probability epsilon 1. Player 2 also announces a posture simultaneously, and he becomes committed to his posture with probability epsilon 2. The definitions of a player's Maxmin payoff and posture are analogous in this case to as they were in the one-sided model. And the result here is that player i's Maxmin payoff, when the commitment probabilities are epsilon I and epsilon j, is exactly 1 minus epsilon j, the probability that her opponent's not committed, times ui star of epsilon I, her Maxmin payoff in the case of one-sided commitment, when her commitment probability is epsilon I. And in addition, a player's Maxmin posture in the case of two-sided commitment is exactly the same as in the case of one-sided commitment. So what's going on here is simply that in the event that player J is committed to his announced bargaining posture, player I can't guarantee herself anything. Player 2, for example, could demand the entire surplus. If he's committed to this, then player 1 can't get anything. So therefore, in order to guarantee herself as much as possible, player 1 just needs to condition on the event that her opponent's not committed, and this is exactly the problem she faced in the one-sided model. An implication of this is that each player's maximum payoff is approximately the same in the two-sided model as in the one-sided model, as long as the player's commitment probabilities are small. So you can see that here, a player's commitment probability is 1 minus epsilon j over 1 minus log epsilon I. If epsilon I and epsilon j are both small, this is very close to 1 over 1 minus log epsilon I. For example, I said that a player could guarantee yourself 13% of the surplus for a commitment probability is 1 in 1,000. 1 minus 1 over 1,000 times 13% is still about 13%. So this shows that essentially the results of the one-sided commitment model carry over without much modification to the case where both players announce bargaining postures. Okay. Okay, so to conclude today, I've talked about a fairly standard model of reputational bargaining where each player announces a partially credible bargaining posture. But I've asked a new set of questions about this model. So rather than asking what happens in equilibrium, I've asked what payoff is each player guaranteed to receive and what bargaining posture for each player guarantees her as much as possible. I've shown that a player can guarantee herself a relatively large share of the surplus even if her commitment probability is very small, and that in addition, the unique way that she can do this is by announcing the bargaining posture that demands this share of the surplus plus compensation for delay in reaching agreement. In addition, I showed that these results extend to the case where both players announce bargaining postures, and in the paper I also showed these results extend to any discrete-time bargaining procedure where both players make offers frequently. And I think I'm out of time, so I think I'll stop here. Thanks.
So when I look at this, it looks sort of like, it seems to mimic what people may do in court cases and maybe sort of unions do, even though I actually have seen very few unions asking for more and more to compensate.
Oh, they do.
But anyhow, it's not what I have seen when, if you and I bargain over a car, if I want to buy a house from you, I've never seen people asking sort of for more as time goes on, or the other way around, that I as a buyer sort of say, well, today I accept, but today I accept sort of you offer minus 10% and tomorrow minus 9%.
Right. So I think there are two things to say here. So the first is that, in any bargaining situation, there's a lot of things going on. So, one thing that's going on is that I'm screening you over time. As you reject my demand, maybe I learn that actually you value it less than I thought you did, and this makes me want to moderate my demand. That sort of learning is not present here at all. So that's the first thing, is just that there are a lot of things going on in bargaining. Here I'm focusing on one aspect of bargaining, this sort of strategic posturing at the beginning of the game that I think hasn't received as much attention in the past, but it's not to say these other things aren't also important. The second thing to say is that the bargaining posture that I identify here is the posture that guarantees you the highest share of the surplus. It's also the optimal posture if I'm pessimistic about your beliefs, but of course it's not the optimal bargaining posture for me to announce if I'm, say, optimistic about your beliefs. If I think that you think that I'm going to be very tough, then maybe I should demand more initially. So you should expect this bargaining posture to be adopted only by bargainers who are pessimistic. If bargainers are more optimistic, they might adopt different bargaining postures. On the other hand, they still always will be guaranteed to receive at least their Maxmin payoff. So that prediction sort of you expect to see hold in all bargaining interactions. This posture you expect to be adopted by pessimistic bargainers, but not by bargainers with different beliefs.
Epsilon, if I understood, played two roles over here. One was it's what you know about me, and the other was it was actually determining the probability with which I decide to take an irrational position or commit to mine. So does it have to be the same, these two quantities?
Right, exactly. So it doesn't, and what's relevant here is the first one. Right, so this was sort of like the question that came up earlier. In order to guarantee myself as much as possible, whatever bargaining posture I announce, I always want to stick with that posture for sure. So actually, I don't care what the probability is that I become committed to that, because I want to, in order to guarantee as much as possible, I want to stick with that anyway. What's crucial for determining how much I can guarantee myself is the probability that you believe that I'm actually going to play this way. And so, in a sense, like that's the real role that epsilon's playing in this analysis.
However, the bargaining posture or the amount that I'm asking for does depend on the epsilon that I believe I'll be committed to. Right?
No. So again, all that matters is your belief. If you could separate those two roles, it would be the first role that would matter for both the payoff and the posture.
So you're taking epsilon as fixed.
Right.
Your analysis reveals that if I'm a bargainer, I want epsilon to be 1. Is that right?
Exactly. So I always would do well if you thought that whatever I announced was a take it or leave it offer. So this does open the door to sort of thinking about maybe if I could invest in my credibility or what actions I could take in some prior game to increase my credibility. I would always want to take those actions, and you could consider a sort of subsequent analysis thinking about those things.
And the guaranteed thing is 0.
Right, exactly. So something I didn't quite have time to flesh out is that in the case of two-sided commitment, I always do better when my commitment probability is higher, but I'd like yours to be lower. Right, when the higher is right. So this number is always increasing in epsilon I and decreasing in epsilon j.
So how does that help us to understand what people should do to affect their epsilons?
Well, I don't know. I think so. Actually, this actually goes back very close to say what Schelling was talking about. You always do better when your announcement is more credible and when your opponent's announcement is less credible. So you'd want to do things to sort of build up your credibility and undermine his.
Although if everybody does that, then the payoff is 0.
You mean like if both, right, so if epsilon I equals epsilon j, this is non-monotone in epsilon. Right, if both of our commitment probabilities are 0, neither of us are guaranteed anything. If both of our commitment probabilities are 1, neither of us are guaranteed anything. Something to note though here is that the case that I'm sort of thinking about is where epsilon is small. In that case, this is going to be increasing in epsilon. So in that sense, two more credible bargainers would both expect more out of the negotiation, in a sense because the scope for pessimism there is lower. But of course, that's not true when these commitment probabilities go to 1, but that's not the case that we think is sort of most salient. Any further questions? Yeah.
So there can be a possible extension where your posture affects the belief about that your opponent has about your commitment power.
Right.
So did you think about any possible extensions like
Right,
that?
so the question is what if this credibility epsilon depends on what posture you announce? So I think again there are two things to say there. So the first is that the techniques I develop here give you the answer how much I'm guaranteed for any posture and commitment probability. So you could certainly use these techniques to answer that question in the more general model. On the other hand, if my credibility depended on my announcement in some complicated way, it might be hard to answer that question sharply. The second thing to say, though, is that the posture that comes out of here is actually quite simple. This posture of demanding this fixed amount plus compensation for delay is relatively simple. And so if more complicated postures than that were less credible, then that would still be the posture that you'd want to announce to guarantee yourself as much as possible.
Okay, so Alex is going to be around for the day, and of course he's next door all the time. So, okay, thank you.